Welcome. Today we're diving into the fascinating world of neutrons. Neutrons are one of the fundamental building blocks of matter, yet they often go unnoticed compared to their more famous siblings, protons and electrons. But what exactly is a neutron? Why is it so important in the structure of atoms? In this video, we'll explore the nature, discovery, and significance of neutrons and see how they shape the universe around us. Let's begin our journey by understanding where neutrons fit in the atomic landscape. Before we focus on neutrons, let's quickly review the basic structure of an atom. Atoms are made up of a central nucleus, which contains protons and neutrons surrounded by a cloud of electrons. Protons carry a positive charge, electrons are negatively charged, and neutrons, as their name suggests, are neutral. This balance of particles determines the identity and properties of each element. Understanding this structure is key to appreciating the neutron's unique role. Neutron was discovered in 1932 by British physicist James Chadwick. Before this discovery, scientists struggled to explain why atoms were heavier than the total mass of their protons and electrons. Chadwick's experiments revealed the existence of a neutral particle within the nucleus, solving this mystery. The discovery of the neutron was a major breakthrough, opening new doors in nuclear physics and chemistry. A neutron is a subatomic particle found in the nucleus of atoms. It has no electric charge, which is why it's called a neutron. Despite being neutral, it has a mass almost equal to that of a proton. Neutrons, along with protons, make up nearly all the mass of an atom. Their presence is crucial for the stability of most atomic nuclei. Like protons and electrons, neutrons do not have an electric charge. This neutrality allows neutrons to interact differently within the nucleus and with other particles. Their lack of charge means they aren't repelled or attracted by electric forces, which is essential for the stability of atoms and for certain nuclear reactions. Neutrons and protons are often called nucleons because they both reside in the atomic nucleus. While protons define the element's identity, neutrons help determine its isotope. The number of neutrons can vary even within atoms of the same element, leading to different isotopes with unique properties. Isotopes are atoms of the same element that have different numbers of neutrons. For example, carbon-12 and carbon-14 are both carbon atoms, but carbon-14 has two more neutrons. This difference can make isotopes stable or unstable, and some isotopes are radioactive, which has important applications in science and medicine. The number of neutrons in a nucleus is crucial for its stability. Too few or too many neutrons can make a nucleus unstable, leading to radioactive decay. Stable nuclei have the right balance of protons and neutrons, which prevents them from breaking apart. This balance is why neutrons are so important in the natural world. When a nucleus is unstable, it can undergo radioactive decay. This process often involves the transformation of a neutron into a proton, or vice versa, releasing energy and particles. Radioactive decay is a natural process that powers the heat inside the Earth and is used in medical treatments and dating ancient artifacts. A neutron's mass is slightly greater than that of a proton, but the difference is tiny. This small difference plays a big role in nuclear reactions and the stability of atoms. The mass of neutrons and protons together accounts for nearly all the mass of ordinary matter in the universe. Neutrons are key players in nuclear reactions. Because they have no charge, they can penetrate atomic nuclei more easily than protons. This property makes them essential in nuclear fission, where a neutron strikes a heavy nucleus, causing it to split and release energy. This process powers nuclear reactors and atomic bombs. Nuclear fission is a process where a heavy nucleus splits into two smaller nuclei, releasing energy and more neutrons. These released neutrons can trigger further fission reactions, creating a chain reaction. This principle is the basis for nuclear power plants and atomic weapons. A chain reaction occurs when the neutrons produced by one fission event cause additional fission events. This can lead to a rapid release of energy if not controlled. In nuclear reactors, control rods are used to absorb excess neutrons and keep the reaction steady and safe. Neutrons also play a role in nuclear fusion, where light nuclei combine to form heavier ones. Fusion is the process that powers the sun and stars, releasing enormous amounts of energy. Neutrons produced in fusion reactions help sustain the process and carry away energy. A free neutron, one not bound inside a nucleus, is unstable and decays into a proton, electron, and antineutrino after about 15 minutes. This property is important in understanding the early universe and the formation of elements after the Big Bang. Neutrons are not just found in atoms on Earth. In the universe, they play a key role in the life and death of stars. In supernova explosions, huge numbers of neutrons are released, and in neutron stars, matter is packed so densely that only neutrons remain. Neutron stars are the remnants of massive stars that have exploded in supernovae. These stars are incredibly dense, with a mass greater than the Sun packed into a sphere just a few kilometers wide. In neutron stars, gravity is so strong that protons and electrons combine to form neutrons. Shortly after the Big Bang, the universe was filled with a hot soup of particles, including neutrons and protons. As the universe cooled, neutrons combined with protons to form the first atomic nuclei. This process set the stage for the formation of all elements we see today. Neutrons have important applications in medicine. For example, neutron radiation is used in cancer treatments to target and destroy tumor cells. Neutron imaging is also used to see inside objects, providing valuable information for doctors and researchers. Neutron scattering is a powerful technique used by scientists to study the structure of materials. By observing how neutrons bounce off atoms, researchers can learn about the arrangement of atoms and molecules in solids and liquids. This method is essential in materials science and chemistry. Neutron activation analysis is a technique that uses neutrons to identify the elements in a sample. When a sample is bombarded with neutrons, some atoms become radioactive and emit characteristic radiation. By measuring this radiation, scientists can determine the sample's composition with great accuracy. Neutrons are used in various industries for quality control and research. For example, neutron radiography helps inspect the integrity of airplane parts and other machinery. This non-destructive testing method ensures safety and reliability in manufacturing. To use neutrons in experiments and applications, scientists need neutron sources. These can be nuclear reactors, particle accelerators, or radioactive materials that emit neutrons. Each source has its own advantages and is chosen based on the needs of the experiment. Detecting neutrons is a challenge because they have no charge. Special detectors are used to sense the presence of neutrons, often by observing their interactions with other materials. These detectors are crucial in research, medicine, and nuclear safety. Because neutron radiation can be harmful, safety measures are essential when working with neutron sources. Shielding materials like concrete and water are used to absorb neutrons and protect people. Proper training and equipment ensure safe handling in laboratories and power plants. While we don't encounter free neutrons in daily life, their effects are all around us. From the stability of the elements in our bodies to the technologies powered by nuclear energy, neutrons play a silent but vital role in modern society. In chemistry, neutrons help determine the properties of elements and compounds. The number of neutrons affects atomic mass and can influence chemical behavior, especially in isotopes. This is why chemists pay close attention to neutron numbers when studying reactions and materials. The periodic table organizes elements by their atomic number, which is the number of protons. However, the number of neutrons can vary, creating different isotopes for each element. This diversity adds richness to the periodic table and the world of chemistry. In physics, neutrons are essential for understanding the forces that hold atomic nuclei together. The strong nuclear force binds protons and neutrons, overcoming the repulsion between positively charged protons. Studying neutrons helps physicists unlock the secrets of matter and the universe. Even though neutrons have no electric charge, they do have a magnetic moment. This means they behave like tiny magnets, which is important in certain experiments and technologies such as magnetic resonance imaging (MRI) and neutron scattering studies. For every particle, there is an antiparticle. The antineutron is the antimatter counterpart of the neutron. When a neutron and an antineutron meet, they annihilate each other, releasing energy. Studying these particles helps scientists understand the fundamental symmetries of the universe. In particle physics, neutrons are made up of even smaller particles called quarks. Specifically, a neutron consists of two down quarks and one up quark. The study of quarks and how they interact is a major focus of modern physics, deepening our understanding of matter. The standard model of particle physics describes the fundamental particles and forces in the universe. Neutrons, along with protons and electrons, are part of this model. Understanding neutrons helps scientists test and refine the standard model, searching for new physics beyond it. Around the world, there are specialized research facilities dedicated to studying neutrons. These include neutron sources, detectors, and laboratories where scientists conduct experiments to unlock new knowledge about matter and energy. In cosmology, neutrons help explain the formation of elements in stars and the early universe. Their behavior during the first moments after the Big Bang influenced the abundance of hydrogen, helium, and other elements, shaping the cosmos as we know it. Some theories suggest that studying neutrons could help us understand dark matter, the mysterious substance that makes up most of the universe's mass. Experiments with neutrons may reveal new particles or forces that could explain dark matter's elusive nature. Neutron detectors are used in space missions to study the composition of planets and moons. By measuring neutron emissions, scientists can detect water and other elements beneath the surface, aiding the search for life and resources in space. Neutrons are central to nuclear energy production. In both fission and fusion, the behavior of neutrons determines the efficiency and safety of power generation. Advances in neutron science could lead to cleaner and more sustainable energy sources in the future. Neutron techniques are used to study environmental samples such as soil and water to detect pollutants and understand ecological processes. This helps scientists monitor pollution and develop strategies for environmental protection. Archaeologists use neutron analysis to study ancient artifacts without damaging them. Neutron imaging can reveal hidden features and compositions, providing valuable insights into history and culture. In food science, neutrons are used to analyze the composition and structure of food products. This helps improve food quality, safety, and shelf life, benefiting both producers and consumers. Neutron scanning is used in security to detect explosives and contraband in luggage and cargo. This technology enhances safety at airports and borders, making travel and trade more secure. As technology advances, new uses for neutrons are being discovered. From quantum computing to advanced materials, neutrons will continue to play a key role in science and industry. The future holds exciting possibilities for neutron research. To sum up, neutrons are fundamental to the structure of matter, the stability of atoms, and countless applications in science, medicine, and industry. Their unique properties make them indispensable in our quest to understand and improve the world around us. As we continue to explore the mysteries of the universe, neutrons will remain at the forefront of discovery. Whether in the heart of atoms, the depths of space, or the cutting edge of technology, the story of the neutron is far from over. Thanks for joining us on this journey through the world of neutrons.